Okay, so let's continue talking about the first law of thermodynamics for open systems. Let me start by giving you a list of some devices that we're going to be analyzing using the first law of thermodynamics. So, and this list is for devices that we're going to look at while they operate in steady flow. So as you recall, steady flow means that there is no time variation of any of the properties inside the control volume. So the list starts with heat exchangers. Then we have turbines, which are generally designed to produce power. Pumps, whose main objective is to increase pressure. Compressors, which are also designed to increase pressure. The difference between pumps and compressors is that pumps operate with a liquid while compressors operate with a gas. Then we have nozzles, which are devices that increase the kinetic energy of a fluid. Diffusers, who do the opposite. They reduce the kinetic energy of a fluid. And then throttling devices, which are mainly designed to reduce the pressure of a certain flow. Those are the ones that we're going to be concentrating on. However, if you look in your text, you will see a more complete list. So I have this table, which might be a little bit too small of a font for you to read, but let me just zoom in. This table is in your text and lists a, let me make sure, no, that's probably a little better. It lists quite a few other devices, many of them that we won't be looking at, but some of the ones that I already had in my smaller list. And another good thing that you should look at when you look at this table, in addition to giving you the name of the device and telling you what the purpose of the device is, it will also give you typical assumptions that are made in applying the first law of thermodynamics to that device. For example, if I look at any of these, let's say, for example, I pick the compressor. As I said earlier, its main purpose is to bring a substance, in this case typically it would be a liquid, to a higher pressure. And it tells you that a common assumption would be to set Q equal to 0, Q being the heat transfer. So that means that you can usually solve an equation, the first law of thermodynamics for a pump, by assuming that there is no heat transfer. And so on. If you look at, let's look for example down here at the turbine, which is the last one that I listed with a red arrow. Its purpose is to create shaft work, that is to deliver a certain amount of work that is useful to us. And again, a common assumption is that there is no heat transfer. That means that the turbine operates while being insulated from the surroundings. This will be more evident as we solve some problems. But let's go in order here now. Let me go back to this figure where I have my list. The first thing that you should always examine is the equation of conservation of mass. And that's, of course, a fairly simple equation from what we saw last time. So we write it as the time rate of variation of the mass inside the control volume is equal to any rate of addition of mass, m dot I for m dot in, and then minus any rate of mass that is exiting the control volume. So that's m dot E. So I for inlet, E for exit. Now, because we are looking at devices that operate in steady state, and remembering that steady state means that there is no time variation of properties inside the control volume, then the mass inside the control volume should not change with time, and then we can eliminate the time derivative. And if we do that, we reach a simpler equation, which of course simply states that any rate of mass going into the control volume should be equal to the rate at which mass is exiting the control volume. So that's very simple. Let's look at an example. In this case, for a turbine. So here is a turbine. Here is a schematic of a turbine. And this turbine, we're told, is operating in steady state. And we're given some information, some data about the operating conditions of this turbine. We know, for example, what the mass flow rate into the turbine is. So we know that it's 1.5 kilograms. And I think this is a water turbine. So 1.5 kilograms going in. As you can see, if you look at the exit, is the same, which is, of course, in agreement with the conservation of mass equation that we just looked at. Then we have the pressure at the inlet, 2 megapascals. We have the temperature at the inlet, 350 Celsius. We also know the velocity at which the fluid is going into the turbine. And you can see that is here, V sub I for velocity at the inlet, 50 meters per second. We're also given the height with respect to some arbitrary reference level of the location of the inlet port. So that's 6 meters above that reference level. I told you we have the exiting mass. We have also the pressure at the exit. You can see it's 0.1 megapascals, much lower than the inlet. That's typical for this type of a turbine. Notice that this is atmospheric pressure. We know the quality of the fluid exiting the turbine, in this case 100%, so the fluid is coming out as saturated vapor. We also know the velocity at which the fluid exits the turbine, 100 meters per second. And again, we have the height of the exit port located 3 meters above an arbitrary reference level. That's the data that is given to us. And then we are asked to determine the power that is produced by this turbine. As you can see, there is a shaft coming out of the turbine, it's rotating, and is delivering a certain amount of power. Another piece of data here is that there is some heat loss from the turbine to the surroundings. And that's denoted here by this quantity minus Q dot. It's negative because, remember, our sign convention tells us that any heat leaving the system is negative in sign. And we know the amount. We know it's 8.5 kilowatts. So note, first of all, that when we looked at the table of typical assumptions for these devices, the last one that I showed you for the turbine, zoom in here, it says that a common assumption is to say that the heat transfer is 0. And while that is a common assumption, you can see that in this particular problem, we're not making that assumption, because in this particular problem, we're actually told that there is a certain amount of heat loss to the surroundings. So how do we tackle this problem? Well, the first thing, of course, is to go back to this, just to verify. Always look at conservation of mass first. In this case, it tells you that the inlet mass flow rate must be equal to the outlet mass flow rate, and that's already verified, so we don't really need to go over that equation again. It's given here that those two are equal. So the next thing would be to look at the first law of thermodynamics, as we derived it last time for an open system, and that is written here. So here is the first law. For a control volume or for an open system with all of its terms. So again, the left-hand side is the rate at which the total amount of energy is changing inside the control volume, equal right-hand side the rate at which heat is being added to the control volume minus the rate at which work is being done by our system inside the control volume, and then the flow terms. So positive inlet mass flow rate times this parenthesis quantity, which is enthalpy, kinetic energy, potential energy, and any other form of energy that might be present with the incoming mass flow rate, and then subtracting the exit mass flow rate times a parenthesis very similar to the other one, except that it has the exit value. So exit value of the enthalpy, kinetic energy, potential energy, and other forms of energy. That's our full statement of the first law of thermodynamics for a control volume. But again, since we are assuming that this device is operating in steady state, I have already crossed out the left-hand side. There are no variations of the total amount of energy inside the control volume. All right, so the next thing that I will do, just so you can see it, because it's a common assumption, although we won't be using it for this problem, but in general, you may make the assumption that kinetic energy, potential energy, and other forms of energy are negligible. That will be a common assumption for us to make. I won't make it in connection to the problem that we're going to solve, just to show you that indeed those variations in those quantities are small. So if we do make the assumption that kinetic energy, potential energy, and any other form of energy variation is negligible, then this equation, of course, loses the last three terms inside the parentheses, and we're left with this, which is a typical expression for the first law of thermodynamics for a steady state operating device neglecting those forms of energy. So we have mass flow rate at the inlet times enthalpy at the inlet minus mass flow rate at the exit times enthalpy of the exit plus heat transfer rate in minus work rate out. Must be equal to 0. So now coming back to our problem, you notice that in our problem we're actually given the velocity at the inlet and the outlet, and we're also given the heights at the inlet and the outlet. That's an indication that we should not neglect kinetic energy or potential energy until we at least check the magnitude of those terms. So we're going to keep them in, meaning that I'm not going to neglect these two terms. I will neglect any other form of energy because there is none obviously present. So any other form of energy I will put to 0. Okay, so let's go then through the numbers for this problem. Again, the question for us is to determine the power produced by the turbine, and the data was given on the figure that we just saw. As I told you, always look at conservation of mass first. In this case, as I said, it's given, so conservation of mass is already checked for us. Then go ahead and write the first law of thermodynamics, which is there. For a steady state, you can see the transient term is gone, but all the other terms are still here. And I have already solved for the power produced by the turbine by leaving it alone on the left-hand side. And then we need to evaluate the right-hand side. So what do we need? Remember, the heat transfer rate was given to us. So that we have is the 8.5 kilowatts going out of the turbine. We have that. The mass flow rate we have. And it's the same for inlet and outlet. So you can see how I have combined the inlet and outlet terms here inside the parentheses. So now I need the enthalpy at the inlet and the enthalpy at the outlet. And then, of course, the kinetic energy at the inlet, at the outlet, potential energy at the inlet, potential energy at the outlet. These are, of course, per unit mass. All of the quantities inside the parentheses are intensive per unit mass. Looking ahead, we know that we can compute the kinetic energies because we have the velocities, and we can compute the potential energies because we have the heights. So the only thing that is really left is these enthalpies. And as I note here, we can get those enthalpies at the inlet and the outlet from the water tables. So remember, the what was given to us was the pressure at the inlet, 2 megapascals, temperature at the inlet, 350 Celsius. Then it should be now easy for you to determine that this corresponds to superheated water vapor. So you have to go to the superheater table and get the enthalpy that corresponds to that pressure and temperature, and that happens to be 37 kilojoules per kilogram. You do the same thing at the exit with a given pressure of 0.1 megapascals, the quality 100%, so we know this is in the saturated table. This is purely saturated vapor. We can read the value of the enthalpy just going in with that pressure. It would be the H sub G in the table. So H sub E is the H sub G at 0.1 megapascals, and you get that number from the table. So now we really have everything. There is nothing really confusing about this problem, but here are the numbers. I just want you to take a look at the numbers that we get. The minus 8.5 kilowatts is the heat loss. Shrink this a little. The heat loss, so that's negative. That's given. The mass flow rate was 1.5, and then the enthalpy is already subtracted. H sub I minus H sub E gave me 461 kilojoules per kilogram. The kinetic energy is here. So 50 meters per second was the inlet velocity squared. I'm sorry, the outlet velocity. 100 meters per second was the inlet velocity. I square that. I have to divide by 1,000 because I need to convert to kilojoules per kilogram. So that's the 1,000 there. And the same thing for the potential energy once you evaluate Z sub I minus Z sub E. You get that. So look at the numbers now. This is 461 kilojoules per kilogram is the variation in enthalpy. The variation in kinetic energy is minus 3.7 kilojoules per kilogram, while the variation in potential energy is 0.03 kilojoules per kilogram. And as you can see, the potential energy is very small. The potential energy variation is very small. We can clearly neglect it, 0.03 compared to 461. But even the kinetic energy variation can be neglected. At 3.7 kilojoules per kilogram is not even 1% of this delta H variation. So neglecting kinetic energy and potential energy is a safe assumption for a turbine like the one we are operating with here. Just because the enthalpy variation is so much larger than those two. So if you just do all the numbers, you get that the power produced by the turbine is 677 kilowatts. And then you can see also here why the table that we were looking at earlier indicates that heat transfer may be neglected. This example shows you that the total heat loss from the turbine is a little bit more than 1% of the total power production. So again, if we had neglected the heat transfer, we would get a result that is perhaps somewhere around 1.5% different. That's not a very significant difference. So by keeping all of the numbers, by not neglecting anything a priori in this problem, we have actually seen how the typical numbers for a problem work out in such a way that it is safe to make the assumptions of neglecting kinetic energy, potential energy, and heat transfer for such a turbine. If we had done that from the beginning, then of course this equation here would have only had the power term on the left-hand side and then the mass flow rate term times the enthalpy difference. That would be all that is left. And that's actually the most common way of tackling a problem like this, if you make those assumptions. Okay, let's look at another problem. And this one is a slightly different one. In this case, this is problem 436 in chapter 4. So what we have is the following. We have a liquid water coming in through this line and going into this so-called flash chamber. So a flash chamber operates by throttling the liquid through this valve so that that significant drop in pressure makes some of the liquid turn into vapor. So comes in as pure liquid, goes through the throttle device, flashes, some of it turns into vapor, and of course some remains as liquid. And then if we want, we can separate now the liquid, take it out one direction while we take the vapor out in some other direction. So what is given to us is the properties of the incoming liquid water. So we have that is coming at 180 degrees Celsius and 2,000 kilopascals. And then we're asked to find the quality of the resulting mixture. That's what the problem is asking us to do. Okay, so how do we solve this? In fact, I thought I would just work it out. We're going to make the assumption that the device is operating in steady state. That's all we know how to do at this point. So this is operating in steady state. There are no time variations. So I'll make that assumption. Assume steady state. The conditions at the inlet are 180 degrees Celsius and 2,000 kilopascals. By now you probably know that this is compressed liquid because of that very high pressure, but if you don't, then you go to the table and look at for example, if you didn't know, you would go into the table at 180 Celsius and find that the saturation pressure is 1,002.2 kilopascals. And our pressure is higher, so that means that this is compressed liquid. So now we know that this is compressed liquid. And if this is compressed liquid, then of course the next thing would be to go to the compressed liquid table to get the data that we need. And so if I go here, remember the pressure is 2,000 kilopascals. So I would go to this table on page 790, and then I would look at this subtable, which is for 2,000 kilopascals, and look under my temperature, which is 180. So 180, and I need the enthalpy, so I pick this number right here, 673.7. I'm sorry, 763.7. So H is 763.7. 763.7, and those are kilojoules per kilogram. Okay? And that's the inlet. So I have that enthalpy at the inlet. Okay, so let me draw again here that first part of the problem. So here's the line, here is the valve, and what is coming out, of course, is the flashed fluid. So the liquid is coming in, this is the inlet, and I look at the exit on this side. Okay, so clearly mass flow rate is not an issue. Whatever mass flow rate is coming in here is also coming out here. So I can write that mass conservation would tell me that m dot inlet must be equal to m dot exit. But again, that's not needed for this particular problem. And then I go and look at the first law. So what happens to my first law equation? Let's go back and look at the full equation. Maybe from this example, from this equation. So we have it right there at the top. That's our full equation. And again, we're talking about steady state. So in steady state, we'll cross out the time derivative term. In this problem, we are going to neglect kinetic energy, potential energy, and any other form of energy. So we'll also cross those out. And then what happens is that as the fluid goes through the valve, there is no work. So if for this part of the problem, I consider my system, the fluid as it goes through the valve, then it is clear that there is no work. There is no rate of work being done. And also, typically, a throttling device would be a small device. There is not a lot of surface area for heat transfer to occur. The fluid goes very fast through the valve. So another very common assumption is to say that there is no heat transfer. And you can probably verify that those are indeed the assumptions if you come down here at the bottom of this chart that we looked at a while ago. The very last entry for a valve, I actually mark here the throttle, but you can see throttle is same as a valve. So for the valve, you can see how there is no work, there are no moving parts, and also an assumption commonly made, there is no heat transfer. So my assumptions are in agreement with what is suggested in a table like that: no work, no heat transfer, and then no other forms of energy. So all that we have left then, if we cross the heat transfer term out, the work term out, and the other forms of energy, kinetic potential and other forms, all we have, of course, is the enthalpies at the inlet and the outlet. So all we have left for the first law is m dot in h in equals m dot out or exit h exit. And since these are the same, m dot in is equal to m dot exit, then the equation, of course, is simply that the enthalpy at the inlet and the exit are the same. This is a typical result for something like a valve or a throttling device. So the enthalpies are the same at the inlet and the outlet. So what that means for us then is that as the fluid goes through the valve, before it enters the tank, the chamber itself, so it flashes as it goes through the valve. We'll see that in a moment. And it comes out on the exit side with the same enthalpy. So these two enthalpies then are the same, and I already got that number up here for the enthalpy. So what I know now is that at the exit, the enthalpy is the same as at the inlet, and that number was 763.7 kilojoules per kilogram. And what else do I know about the exit? That's listed here also in this cartoon. We know that the pressure in the chamber here is 500 kilopascals. So of course that's the pressure on the backside of the valve. So we know that here too, so we can write that here. P at the exit is 500 kilopascals. So now we have two data points for the exit fluid. We know its enthalpy, and we know its pressure. And from the state postulate, we know that's enough for us to determine the state at the outlet. So how do we know then that this is saturated vapor, as the problem implies, because it tells you to find the quality in the chamber? Well, you could go back to the table, and in this case, you could go back to the saturated table, but you would go to the pressure entry. So table B12, and you need to enter that table at 500 kilopascals, because that's our pressure. So if I enter that table at 500 kilopascals, it's actually here near the bottom. So I have 500 kilopascals. I need to enter there. And then I need to go all the way to the enthalpy columns, which are these three: HF, HFG, and HG. And what I need to see is if my enthalpy is in this range from 640 to 2748. And of course it is, because our enthalpy is 763.7. So, but I need to take these numbers down. In fact, I will take the HF, now that I have already checked that is in the range, 640 is larger than 640 but smaller than 2748. I will take the 640.21. So I know that HF is 640.2 kilojoules per kilogram, and I will also take HFG, and HFG is 2108.5. 2108.5 kilojoules per kilogram. And then, of course, I know that the total enthalpy of the mixture is HF plus quality HFG, from where I can now solve for the quality. So I can go quality is H minus HF over HFG. And all of these numbers are given. This H, of course, is the H at the exit. So I have that 763.7. I just wrote down HF and HFG, so I can put in all those numbers and come up with the quality. I will just let you, I just put here a check mark that we can get that number and let you work it out, so then you can get a final number. But now we have a mixture of liquid and vapor at the exit, and that's what is here in the tank. Okay. Let's see. What are we doing on time? 3:35. Let's look at another type of problem. Let's look at the second type of problems. Let me go back here to something, let's see. Should be here. The types of problems that we are looking at. If I can find that slide. Well, I guess I'll write this. Oh, I'm sorry, here it is. So, we were going to look at two types of processes for control volumes or open systems. The first one, the steady state process, which we just saw a couple of examples. And then the second type of problems, which are the so-called transient problems. So let's look at those next. As the name implies, what is happening is that now we cannot make the assumption of steady state. So when we wrote the first law of thermodynamics in general for a control volume with all of the terms, the problems that we have done so far are such that the energy inside the control volume was constant in time, and therefore its time derivative was 0. But now we're going to remove that assumption and look at the so-called transient processes, number 2 here on this list. So transient processes, of course, are processes where the conditions inside the system are changing in time. A common example is something like this, where you have a tank that is being filled. And I have a figure here somewhere, if I can find it. Let's see. Should be right here. So this is a typical transient problem. There is a tank which is initially empty, and this tank is connected to a line. Through this line, there is a continuous flow, and then there is a valve. And so, for example, if we open the valve, then the tank will get filled. So some of the fluid will go in, and this tank in here will go from an initial condition where it was empty to a final condition where it is holding some fluid at some pressure and some temperature. So clearly, when you look at the control volume, if you can see the control surface there, being this, the contents of this tank, this is no longer a situation where we can assume steady state. Because if you look at the properties inside the control volume, they are changing in time. So we have to go back then to the full equation and not neglect the left-hand side. So let's look at this in detail. Let's see, we already saw that. So for the transient process, the first thing we want to look at is the mass conservation equation. And here is our mass conservation equation with all of its terms. The rate of variation of mass inside the control volume is equal to the rate at which mass is being added minus the rate at which mass is being subtracted. This is the so-called rate form of the equation. Another form of the equation is to actually write it in reference to the initial and final states. So if I call the initial state 1 and the final state 2, then the difference in the amount of mass between final state and initial state must, of course, be equal to the difference between the amount of mass that was added and the amount of mass that was subtracted. Most of the problems that we're going to look at in transient form, we're going to look at them in the so-called integrated form. That is, we'll have to think of a picture of the system at the initial condition, and then a picture of the system at the final condition, and then write our equations in terms of those two states. So here's the first law with all of its terms again. Rate of change of energy inside the control volume, heat transfer, work, the terms associated with the mass flow in, and the terms associated with the mass flow out. So if you now take this equation, which is in rate form, just like this one was here in rate form for mass, this one is in rate form for energy, and you integrate it in time. So let's take this equation and integrate it in time. Then this is what happens. So suppose you multiply times dt and do a time integration. The left-hand side is easy, because if I multiply times dt and integrate from the initial state 1 to the final state 2, then all I have is, of course, is delta E, the total change in energy inside the control volume. The next two terms are also very easy, because if I take the heat transfer rate and I integrate it in time from beginning to end, then I get the total heat transfer from 1 to 2. Again, remember, the rate form of the equation is per unit time, so this Q dot would be, for example, in kilowatts, kilojoules per second. Once I integrate it in time, this is actual total heat transfer Q12. It would be given, for example, in kilojoules. Same thing for the work. Integrate the work rate, you end up with the total work. The next two terms are a little tricky, because only under certain assumptions you can actually carry out the integrals. So I have written both of them here. The integral from 1 to 2, m dot I, all the terms that belong in the parentheses are there. I just wrote the first one, h sub I, plus the other terms. dt, that I am integrating in time, the same thing for the exit. So integral from 1 to 2, m dot E, and then the parenthesis terms, dt. Now, this is not a trivial quantity to integrate unless something happens. So that's what this statement essentially says. If the quantities in parentheses, the h sub I plus the other quantities and the h sub E plus the other quantity vary during the process, these integrals can get complicated. Because that's the only way I can evaluate these integrals, if I know how this integrand changes in time. But here's where we make a very significant assumption for our problems. Put this down. However, if we take the parenthesis quantities to be constants in time, that is, we will make the assumption that the enthalpy, kinetic energy, and potential energy of the fluid coming into the control volume are constants in time. Same thing for the exit quantities. If they are constants in time, then they can, of course, be taken out of the time integrals. So if I make the assumption that these terms in parentheses don't change with time, I can take them out, and then if I take them out of the integrals, the only thing that is left in the integrand is the mass flow rate, m dot. And when I integrate the mass flow rate, of course, I get the mass. So making this assumption allows me to carry out the integrations. This becomes now the total mass that goes into the system, because it has been integrated in time, and this is the total mass that has exited the system. It was the mass flow rate integrated in time. And this version of the equation is our preferred version of the equation for the second law for a transient process. Keep in mind that you need to verify that indeed this assumption is met when you are solving a problem like this. So let's look at an example to see what's happening, to see how that is used. Here is our example. Problem 4.154. We have the following arrangement. We have a cylinder with a piston. There is a set of stops near the top here. And this cylinder is connected through a line that carries air. So air is flowing through this line, and there is a valve that connects the line to the cylinder. And this is what we have. We know the conditions of the air in the line. Keep in mind that indeed the air that flows through the line is flowing in steady state. That is, I have a continuous flow of air along this pipe that is always at a certain pressure and a certain temperature, which are fixed. So I call them P sub L and T sub L, and I assume they're given. So I know those values. All right. I also know the initial conditions of the air. You can see here I drew a red dashed line to denote the boundary of my system. So my system, or my control volume, is inside this dashed line. So it contains air initially, and I know the pressure, the volume, and the temperature of this air. Those are P1, V1, and T1. So those are given as well. And I also know the volume when the piston is at the stops. So if the piston has moved all the way to the top, I also know that volume. So everything that is listed here, P1, V1, T1, volume at the stops, L and TL are given. And this is what happens next. Now we open the valve. Of course, these pressures are different. The pressure inside the cylinder is less than the pressure in the line. The valve is now opened, and we're going to keep it open until the pressure inside the cylinder reaches a new pressure P2 and a new temperature T2. And this pressure P2 is going to be a value that is in between those two. When you actually plug in the numbers for the problem, you will see that the P2 is in between the P1 and the PL, which makes sense. So we're going to open the valve, allow for some of the air to flow into the cylinder. The pressure will rise until a new pressure is reached, but this pressure will be less than the line pressure with the data that are given to us. And then we're asked to determine how much air flowed into the cylinder. We're also asked to determine how much work was done by the air. Remember, the air is going to be pushing this piston up, and in doing so, we'll be doing work. And we're also asked to find out the total heat transfer rate, Q12. So those are our unknowns. With the data given, you can determine that it is fine to treat this as an ideal gas. You'll see the numbers in a second. And so, first question that you should ask yourself, I'm going to go ahead and write the data here. The actual data that is given is P1 300 kilopascals, T1 17 Celsius, V1 0.25 cubic meters. The volume at the stops that is also given is 1 cubic meter. And the pressure in the line is 500 kilopascals. And the temperature in the line is 600 Kelvin. And then after the cylinder is filled, we're going to have a pressure P2 of 400 kilopascals and a temperature T2 of 350 Kelvin. 350 Kelvin. So that's the data. So here you can verify what I said. The initial pressure is 300, the line pressure is 500, the final pressure is in between, is 400. Okay, so when we go back and look at the problem, we ask ourselves, well, I know clearly that once I open this valve and air starts flowing in, this piston is going to move up. The first question that we should ask ourselves is this piston going to reach the stops? Because that will be important. Is piston going to reach the stops? And if you think about this for a moment, you will conclude that the answer is yes. How do I know that the answer is yes? Because This is a free-to-move piston, meaning there is no friction between the piston and the cylinder. And therefore, if you make the assumption of quasi-equilibrium, the pressure on both sides, you do a force balance, assuming that, for example, that you neglect the mass of the piston, or that you don't have to do that. But while the piston is moving up, freely moving up, the pressure will have to be the same. The pressure will have to be constant. So since we know that at the end the pressure is 400 and we started out with a pressure of 300, the conclusion is that this piston must have reached the stops before the end of the process. Otherwise, the pressure couldn't go up from 300 to 400. So if I actually make a plot, if I do a plot on a PV diagram, if I do a plot on a PV diagram, then the first part of the process, as the piston is rising, has to be a constant pressure process. So let's say that this is the initial state 1 inside the control volume, inside this cylinder. Then while the piston rises, I must be going at a constant pressure. And then, of course, at some point I'm going to hit the stops. And once I hit the stops, then the volume can't change anymore. So that's when the pressure will begin to rise. So the next part of the process then will have to be at a constant volume. The piston is at the stops, and it will go up until I reach the given final pressure. So if I put numbers here, this pressure at 1 is 300 kilopascals. So this pressure is in kilopascals. And then this final pressure is 400 kilopascals. The initial volume is, if I put this volume in cubic meters, then this volume here is 0.25, and this volume here has to be the volume at the stops. So this has to be 1 cubic meter. So that would be what my PV diagram would look like. Okay, so how much mass goes in? So I can make the assumption that this is an ideal gas, because my pressures are very low. So if I, for example, look at the components of air, I think of nitrogen. This pressure is 3 atmospheres. This pressure at the end is 4 atmospheres. Those are fairly low pressures that allow us to use the ideal gas law. So if I use ideal gas law, then I can, of course, find the initial mass, because I can write PV equals mRT, where this R is the constant for air. And then if I look at the initial conditions, I have everything except the mass. So I can find the initial mass M1 as P1 V1 over R T1. And all those are given. I don't have the number. I will let you do the actual calculations, but you can find the initial mass. Okay, so now what is our, let's write the mass conservation equation then. If we write mass conservation, and we have the form that we just saw. So if we look at this form of the equation, M2 minus M1 equals Mi minus Me. First of all, we notice there is nothing exiting the cylinder, so Me is 0. And therefore, we can write this as Mi is equal to M2 minus M1. We just calculated M1, and since we're being asked to find Mi, then of course we need to find M2. All right, so how do we find M2? Same way, because we have the final pressure, final temperature, and we know that the final volume is the volume at the stops. So we can also find M2 as P2 V2 over RT2, and we have everything. So we have the mass. We have M1 and we have M2. Now, what about the first law of thermodynamics? Here's our equation for a transient process. We have to check the assumption as to whether, remember, the quantities in parentheses were constants in time. And if we look at this problem, the answer is yes, because the fluid that is going into the tank, the air that is going into the tank, first of all, the line has properties that don't change in time. So the pressure and temperature in the line are fixed. That's not a time-dependent process. As the air goes through the valve, of course, there will be a change in pressure. Pressure will change. But at the same time, I know that the enthalpy, if you think of the example that we solved a moment ago, the enthalpy as I cross the line doesn't change. So as I cross the valve. So the enthalpy at the inlet of the valve is equal to the enthalpy at the exit of the valve. And therefore, the enthalpy that I need for the air going into the tank is not a function of time. So that satisfies our condition to use this equation. So if I just take this equation, and write the terms that I need, I will neglect any other forms of energy. So this is only going to be internal energies. So the total energy is going to be for me. So if I write first law, E2 will be capital U2. E1 will just be internal energy, U1, neglecting kinetic energy and potential energy. I have Q12 that I was asked to determine. I have W12 that I was also asked to determine. And then the only term that I have is, of course, MI times HI. So that's my first law of thermodynamics for this problem. On the left-hand side, these are extensive properties. This is capital U2, capital U1. So I should write those in terms of intensive properties. So capital U2 is M2 lowercase u2. And capital U1 is M1 lowercase u1. Q12, W12, MI, HI. Of course, I know what MI is because I have M1 and M2, and my equation tells me that MI is just the difference of those two. So I know MI. So let me put check marks here around the things that I know. MI, M2, M1. HI I can read in the table because if I go to the air table at the temperature of the line, then I can read the value of enthalpy. So let me write this here on another piece of paper. So let's do HI from ideal gas table for air, right? And you read it with TL, the temperature of the line, because that's your enthalpy at the inlet. So you go to the ideal gas table for air, and that is right here. You go to this table on page 762, ideal gas properties of air. Add your temperature, which is, it was 17 Celsius. Don't forget to convert that temperature to to Kelvin, to an absolute scale. So once you convert it to Kelvin, then you can come into this table with your temperature and read your H, would be the third column. So we can get HI from the table. So I can now put a check mark there. Same thing for U1 and U2. Those are the internal energies of the air. U1 is the internal energy of the air, read in the ideal gas table. Also with my temperature, in this case it would be T1. So I go with T1 into that table and read U1. Same thing for U2. So I read U2 using T2. So with my three temperatures which are given, I can read the enthalpy and internal energies that I need into this equation. So that only leaves two things, the heat transfer and the work. The heat transfer, of course, is one of the questions. We're asked to find the heat transfer. So if we solve for the heat transfer, M2 U2 minus M1 U1 plus W12 minus MI HI. We have all of these quantities except the work. However, the work is easy to find because if you go back to this plot, the work occurs while the piston is moving up, and the piston is moving up at constant pressure. So since the piston is moving up at constant pressure, the work can be easily determined from this graph because the integral of pressure over volume is just going to be this area. So that area is nothing but the work that I am trying to calculate. So this is W12. So that's easy. It's 300 kilopascals times 0.75 meters. So that's now easy to get. I can check that off, and now I can find the Q12. So let's put a check mark here. You can do the numbers on your own and finish the problem that way. Okay, I think I'm going to finish this lecture here, and when we come back next time, we'll start discussing the second law of thermodynamics. Thank you. Bye.